subterranean loop.
That is unbelievable. And because this deep biosphere is powered by planetary geology rather than surface conditions, it represents the ultimate planetary failsafe.
It really is. Think about it.
If the Earth were struck tomorrow by an asteroid 10 times larger than the one that wiped out the dinosaurs, an impact so violent it vaporized the oceans and turned the entire surface into a sea of molten glass, the surface biosphere would be completely annihilated.
Gone in an instant.
But miles underground, the endoliths wouldn't even notice a thing. The rock would still decay, the water would still split, and they would continue their centuries-long metabolic cycles entirely undisturbed.
And this specific mechanism of survival provides us with a clear, actionable instruction manual for astrobiology, particularly concerning Mars.
Yes, Mars.
When we observe Mars today, we see a surface that is incredibly hostile to life. It has a thin atmosphere, no magnetic field, and a surface bombarded by heavy ultraviolet radiation.
It is a dry, freezing, irradiated desert.
But Mars used to be warm and wet. It had flowing rivers and shallow seas billions of years ago.
Right. So if life emerged on the surface of Mars during that temperate period, what would it do as the atmosphere was slowly stripped away and the surface became deadly?
It wouldn't just die out immediately. It would follow the water and the heat. It would retreat underground.
So if Martian life survives today, it is almost certainly endolithic.
Almost certainly. It would be residing miles beneath the irradiated regolith, utilizing the remaining geothermal heat to keep subterranean aquifers liquid and surviving off the hydrogen produced by the radiolysis of Martian rocks.
So to find life on Mars, scratching the surface isn't enough. We literally have to drill deep.
We have to drill.
This brings us to the culmination of our deep dive today. We've mapped out a whole new biological reality, from boiling pressure cookers and frozen brine channels to acid lakes, sugar glass vitrification, and radioactive rock eaters.
We've covered a lot of ground.
But how does this vast array of extreme biological ingenuity actually dictate the day-to-day operations of our space telescopes and planetary rovers right now?
It represents a fundamental paradigm shift in our search parameters. The era of hunting exclusively for Earth twins is over.
We are no longer restricting our gaze to planets with nitrogen-oxygen atmospheres, blue skies, and temperate surface oceans.
Right, because we now recognize that life is not constrained by our narrow comfort zone. We've distilled the recipe for life down to 3 universal, non-negotiable ingredients.
Okay, let's lay these out to the listeners. What's the first ingredient?
The first ingredient is an energy source. The old model demanded a star for photosynthesis. The new model recognizes that geothermal heat, chemical gradients at hydrothermal vents, or even radiolytic decay deep underground are perfectly viable metabolic engines.
Okay, that makes total sense. And the second ingredient?
A suite of basic organic elements: carbon, nitrogen, phosphorus, just the raw building blocks.
And the third ingredient?
A liquid solvent, a medium to facilitate chemical reactions and the transport of nutrients.
No, water is the gold standard for that, right?
It is, because of its unique polar properties and its abundance in the universe. But theoretically, the solvent doesn't strictly have to be water.
Really?
Yeah. We look at a world like Saturn's moon Titan, where the surface temperature is hundreds of degrees below zero. Water is frozen harder than rock there.
But Titan has active weather systems, doesn't it?
It does. It has rivers and lakes, but they're made of liquid methane and ethane.
Wow.
So it is entirely plausible that a radically different biochemistry could utilize liquid hydrocarbons as a solvent instead of water.
So energy, organic building blocks, and a liquid solvent. That triad is the new astrobiological baseline.
Exactly. If an environment possesses those 3, it is a candidate. And the extremophiles on Earth provide us with the specific chemical signatures to actually look for.
Right, because when astronomers point the James Webb Space Telescope at an exoplanet 50 light years away, they obviously can't see the surface.
Yeah, they conduct what's called transmission spectroscopy.
How does that work?
Well, as the exoplanet passes in front of its host star, the starlight filters through the planet's atmosphere. Different chemical molecules absorb different specific wavelengths of light.
Okay.
By analyzing the spectrum of light that makes it to the telescope, astronomers can deduce the exact chemical composition of that alien atmosphere.
They aren't looking for visual evidence. They're looking for biosignatures.
Precisely. They are searching for atmospheric gases that are in severe thermodynamic disequilibrium.
Disequilibrium? Like what?
For example, methane and oxygen react with each other and destroy each other very quickly. So if you find an atmosphere rich in both methane and oxygen, it means something on that planet is actively and continuously pumping massive quantities of those gases into the air faster than they can react.
And on Earth, that something is life.
Exactly. The metabolic byproducts of massive planetary-scale microbial biospheres alter the atmospheric chemistry in measurable ways.
And when we look at our local rovers like Perseverance currently drilling into the Jezero crater on Mars, they're utilizing the specific lessons learned from Earth's deep biosphere too, right?
They absolutely are. They aren't hoping to crack open a rock and find a perfectly fossilized Martian trilobite.
That would be nice, but yeah.
Right. Instead, they're looking for subtle, microscopic, isotopic fractionation.
Okay, unpack that for us.
Well, biological processes are inherently lazy.
Relatable.
Right. They always seek the path of least thermodynamic resistance. So when microbes metabolize carbon, they preferentially process the lighter isotope, carbon-12, over the heavier carbon-13.
Because it requires slightly less energy to break the chemical bonds.
Exactly.
So if a rover analyzes a layer of ancient sedimentary rock and discovers a sudden, localized spike in the ratio of light carbon to heavy carbon,
It is a massive red flag indicating that biological activity occurred there billions of years ago. It's a chemical fingerprint left behind by microbes operating exactly like the extremophiles we study in Earth's harshest environments.
we basically use the survival mechanisms of Earth's toughest organisms as a Rosetta Stone to translate the chemical signals of the cosmos.
That is a perfect way to summarize it.
The shift in perspective here is just profound. Extremophiles have definitively proven that life is not this fragile anomaly clinging to a narrow sliver of perfect conditions.
No, it is an aggressive, adaptive, highly engineered force capable of colonizing and mastering the most violently severe landscapes imaginable.
The line we previously drew to separate habitable from uninhabitable was just an illusion.
Completely. It was an arbitrary boundary defined only by our ignorance of evolutionary ingenuity.
And honestly, this realization instills such a profound sense of optimism about the cosmos. When we look up at the night sky now, at the dark, pressurized subsurface oceans of Europa, the frozen red deserts of Mars, or the thousands of exoplanets orbiting distant stars, we can no longer dismiss them as sterile voids.
We really can't. We know the universe is harsh, but we have empirical proof that life has already figured out how to conquer that highness.
The microbes thriving in our boiling thermal vents, navigating our deep ice, and powering themselves with radioactive rock are undeniable evidence that the universe is likely a vast, interconnected tapestry of extreme habitats.
Teeming with resilient life forms perfectly adapted to their bizarre worlds.
Before we close today's session, I want to leave you, our listener, with a final provocative thought to mull over. We discussed panspermia earlier, the verified reality that organisms like tardigrades and Deinococcus radiodurans possess the exact biological hardware necessary to survive the freezing, irradiated vacuum of space.
And potentially seed new worlds. The mechanisms are undeniable.
Right. So if life is truly this adept at interstellar travel, and if organisms on Earth are already perfectly adapted to survive the worst conditions the cosmos has to offer, what if the extremophiles we find in our deepest, most isolated trenches didn't actually originate here?
That is the big question.
What if Earth didn't meticulously evolve these survivors in some ancient warm pond, but simply caught them?
Wow.
What if they hitched a ride across the solar system on a meteorite billions of years ago, crashed into our oceans, and simply woke up? What if the alien life we are so desperately searching for out in the stars is already here, buried miles beneath our feet, just waiting for us to finally realize where they came from?
It really recontextualizes our entire search. Looking outward into the cosmos might actually be the key to understanding our own deep, potentially extraterrestrial ancestry.
It is a staggering thought. And on that note, we will officially conclude this deep dive. Thank you for joining us on this journey to the absolute fringes of biological reality.
It's an incredible discussion.
The universe is wilder, tougher, and far more crowded than we ever dared to imagine. Warmest farewells to you all, and as always, stay curious until the next session at Stellar Lab.